Okay, so for today, we are talking about the structure analysis of trusses using stiffness methods. Here is a sample of truss, example of truss, consists of 5 members. As you can see on the truss, there is some numbering of the members and numbering of nodes. So the bottom one is member 1, the vertical one to the left, the right is member 2, and the inclined one to the left is member 3, and the inclined one in the middle is member 4, and the top one is member 5. And you can also see the numbering of nodes. Node number 1, 2. The numbering of nodes is in circle 1, 2, and 3, 4. So this truss consists of 4 nodes and 5 members. The numbering of members in a rectangular box, the numbering of nodes in a circle, and you can see at each node we have 2 coordinates of displacement. Like node 1 we have 7 and 8, node 2 3 and 4, node 3 1 and 2, node 4 5 and 6. Okay, what does this numbering mean? The numbering from 1 to 8 is the number of degrees of freedom or the number of unknowns. For trusses, as you know, how many displacement at the node of each truss? We have 2 displacement at the node of each truss of trusses. So the node of truss has 2 displacement, one in x direction, one in y direction. And to the left here, this is x direction, and y direction. This is the positive signs of x and y direction. Okay, but x and y direction are global coordinates. We call them global coordinates. So all the members can fit in this x and y. Okay, so this is generally what we have here in this truss, and we will discuss how to transform the element stiffness matrix in 1D direction to structure global coordinates of system 2D for the truss. Okay, the stiffness matrix we learned last week was for local system. What is the local system? Local system, if you look to the right here, this is our member. This is an example of member 4. If the member is inclined, so we have different we have some differences between the global and the local coordinate system. As you can see here, the member 4 is starting with node 3 and starting from node 2 and end at node 3. So the direction of this member going up like this. If you can see the arrow, so it is going up. The local coordinate system for this member is x bar or x dash and y dash. Can you see x dash and y dash? What is x dash? X dash is the axis or the local axis in the member direction. So x bar or x dash is the axis in the member direction. Y dash is the axis perpendicular to the member direction. So this is the difference between global and local axis. Look, global axis all the time x will be horizontal, y will be vertical. X is going to the right, y is going up. But for local axis or local coordinate system, we have a local system or system of coordinates matching with each member. So this member is inclined, so x dash is inclined because it is axis parallel to the member. Y bar is also different from the global axis and it is perpendicular to the member. Okay, in this lecture we need to know how to convert from local axis to global axis, or how to construct the global coordinate system for the truss. Okay, if you look on the numbering of nodes and the numbering of displacement here, there is some tips to number the nodes or numbering the displacement. If you can see, we have the displacement 1, 2 at node 3, 3 and 4 at node 2, then 5 and 6 at node 4, 7 and 8 at node 1. So the idea of this numbering is to start with the unknowns. As you know, node 3 and node 2 are free nodes, so they will move in X and move in Y. So the displacement 3 and 4, 1 and 2 are unknowns for us. So that's why we start with this 4 unknowns. So we start first with the unknowns 1, 2, 3, 4. Then at support 4, at node 4, we have a roller support. The roller support allow for the displacement or movement in Y direction. So the displacement 5 is unknown for us. So also 5 is unknown. But the roller support prevents the movement in X direction. So 6 is not allowed. The movement in 6 direction is not allowed. So 6 will be known for us and it will be 0. Also at node 1, we have support at node 1, which is hinged support. So the hinged support prevent the movement of node prevent the movement of in X direction and Y direction. So displacement 7 and 8 are 0. So in this truss example, we have unknowns 1, 2, 3, 4, 5, and we have knowns 6, 7, 8. Okay. If we go to the next step or next slide, this is what I was talking about. If we look here, so we have something called degree of freedom or the unknowns of this truss. So we have in this truss 4 degrees of freedom for each truss element, 2 displacement for each truss joint. So at each truss joint or at each truss node, we have 2 displacement or 2 degrees of freedom. The 2 degrees of freedom at 3 are 1 and 2. The 2 degrees of freedom at 2 are 3 and 4. If we have look at member 4, as you can see, this is how they look like. So 1, 2, 3, 4 are movement or displacement of nodes 3 and 2 and 3. Okay, but this movement or displacement are in X direction and Y direction in global system. So this displacement are global displacement or global degrees of freedom. Okay, so for this truss, if we look at how many degrees of freedom we numbering in this truss, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have 8 degrees of freedom. From 1 to 5, as we mentioned, are unknowns because we don't know them. But from 6 to 8, 6, 7, 8 are support constraints, so they are 0. Because the support prevent the movement, so it make the displacement known to us, and the displacement will be 0. So for this truss, how many unknowns or how many degrees of freedom? 5. And how many known constraints or how many known displacement? 3 from 6 to 8. Okay. And this is the displacement and force transformation. So in this section, we will know how to transform the forces and displacement defined in the global coordinates, in the local coordinates to global coordinates. So it is easy for us to deal with the local coordinates because this is how the stiffness method was built on. And then using this local coordinates or local system, we convert it to the global system because we need the final answer in global system, not in local system. Okay, so we will transform the member forces Q. So Q small is the member forces vector, and the displacement is d vector, and the global system is x and y coordinates. Okay, if we look at this truss is another example of truss. We have member NF is an inclined member, for example. It has two angles. The angle with x-axis is theta x. Hopefully you can see the symbols. And the angle between the member and the y-axis is theta y. So we have theta x and theta y. And this member is starting from node N and end at node F. If you can see, the local axes are x dash in the member direction and y dash perpendicular to the member direction. The global axes are x and y, horizontal and vertical axis. Okay. In this figure on the left, on the right, sorry, you can see also how we can get the coordinates in global system. If this our 0 point, this is the intersection between x and y axis. So from 0 to node n in in horizontal direction, this is called xn, the coordinate x of node n. And here at node f, from here to here is the coordinate x for node f. For y direction, we have from here to node n, this is yn. From 0 to f is yf. So we can easily get the coordinate system in global using the dimension given in example or something like this. So you need from this two figure to know what is the sign convention for x axis and y axis in global and local, and how can we find the inclination angle between x and y axis, and how we can get the coordinates for each node of the class using the coordinates global coordinate system. Okay. Now in this step, we need to like derive the equations. If we know the angles and if we know the coordinates, how can we find or how can we convert from the local system to the global system? Okay. In this class, we will assume, to make it easier for us, we will assume cosine theta x is lambda x, cosine theta y is lambda y. So we will deal mostly with cosine. That's why we are having two angles. And what is the relation between the two angles? Do you know what is the relation between the two angles? Is there any relation between the two angles? Theta x and theta y? If we look at these two angles, these two angles together are making a normal angle. So should be theta x plus theta y equal to 90. Okay. We have two angles to make it easier for us in the derivation and deal only with cosine. So we will give cosine theta x symbol lambda x. We will give cosine theta y lambda y, just to make it simple, simplify the derivation. Okay. How can we find theta lambda x and lambda y, or cosine theta x and cosine theta y? Do you have any idea? I can try to work it out with you. Just to give me a second. Okay, can you see my whiteboard screen now? So what I was saying is, if this our member in F member, so we give if this y axis, so this is x axis. Okay, we give this angle the symbol theta x, because it is angle with x-axis, and this angle is theta y. So in our calculation and load calculation, we will need to deal with the horizontal and vertical components of the inclined forces. That's why we need to deal with cosine theta x and cosine theta y. So for simplification, we give theta x, cosine theta x, the symbol lambda x, cosine theta y, the symbol lambda y. From this figure or from this sketch, how can we find lambda x and lambda y? Do you have any idea how to find them? If we are looking to this coordinate system, this is a coordinate system, let's say. This is the 0 point and this x-axis. So from here, this is node n. This is called x of n. And this called x of f. In y direction, this is yf, and this is this is yn. Okay. And this is yf. Okay. So in this angle, in this triangle, this is a normal triangle or normal angle. So how can we find theta x? Cosine theta x. How can we find cosine theta x? Cosine theta x will be the adjacent, this coordinates over this coordinate. So if we find coordinate 1 and coordinate 2, we can find theta lambda x or cosine theta x. So lambda x equal to cosine theta x equal to element 1 over element 2. How can we find 1 and 2? Or let's say L1 and L2. How can we find L1 and L2? If this L1 and L2. This L1 will be equal to from the x coordinate. Can you find it? It will be xf minus xn. Okay. We need another coordinate to help us, so we will need this coordinate as well. So we call it L3. L3 will be yf minus yn. So yf minus yn. So L2 will be from this triangle, it will be root of xf minus xn squared, this Pythagoras rule, plus yf minus yn squared. Okay, so using 1 and 2, we can get lambda x. So from this calculation, lambda x will be equal to cosine theta x and will be xf minus xn divided by root xf minus xn squared plus yf minus yn squared. Okay. It looks complicated just because we are dealing with symbols, but if you have the dimension of this member, so it will be only a number, just a numbers. Okay. This for theta x or for cosine theta x. How about lambda y, which is equal to cosine theta y? How can we find cosine theta y? If we go back here on the top, so in this triangle, this yellow triangle here, we can get cosine theta y. How can we find cosine theta y from this triangle? This is also a normal angle. So we have, this is theta y. So we have this element which is L3, and this element is L2. So if you have a look here, cosine theta y will be L3 divided by L2. Okay, how much L3? L3 will be yf minus yn divided by the root xf minus xn squared plus yf minus yn squared. Okay, so this is how to find cosine theta x and cosine theta y, and we give them the symbols lambda x and lambda y for simplification. Okay, do you have any question about this two, or this derivation of the angles or cosine angles? So we give this equation 1 or step 1. I will go back to the slides. So if you look here, so you can see that xn, that because lambda x equal to xf minus xn, and lambda y will be yf minus yn divided by root xf minus xn squared plus yf minus yn squared. Okay, do you have any question about this two equations or this derivation? Okay, so now the next step, what we benefit from the last step, why we calculate theta, cosine theta x and cosine theta y. In this slide, you will find how to derive the transformation matrix, or how to transfer from the local and get the global stiffness matrix. So this one is how to transform. In global coordinates, we have each node have 2 degrees of freedom. So this is the derivation in like 4 steps, A, B, C, D. At each node, we assume that we have movement in X, and we get the force, or we get the displacement, and we assume a displacement in Y, dny, and get the displacements, and we assume horizontal displacement at F, and we get the displacement. We assume a vertical displacement at Y, dfy, and we get the displacement. So in this one, we just need the final derivation here. So the displacement at node n along the bar is neglecting the change in theta x or theta y will be dn equal to dnx cosine theta x, dny cosine theta y. Okay, what is d small and what is d capital? If you look at the slides, what is the meaning? What is the difference between d small and d capital? Do you have any idea? D is representative for the displacement. D small is the displacement in local coordinates. D capital is the displacement in global coordinates. Okay, if you look at here, if you look at a picture A, dnx in x direction. So it is horizontal in x direction. That's why it is our global coordinates. Here as well, dny capital is the global coordinates in y direction. dfx is the horizontal or in global direction. dfy is the vertical in global direction. So d capital representing the global displacement, d small is representing the local displacement. So the relation between the local and the global displacement is from this 4 picture, dn, this is the displacement at n, equal to dnx cosine theta x, dny cosine theta y. and this is equation 2. And we can replace cosine theta x with lambda x, cosine theta y with lambda y. In similar manner, we can find the displacement at node F along the bar, neglecting the change in theta x or theta y as follows. df is dfx cosine theta x, dfy cosine theta y. Okay? This two equation comes from the analysis of these forces in the member direction. So you can see here, if we analyze the force dnx in the member direction, it will be dnx cosine theta x. And if we analyze dny in the member direction, it will be dny cosine theta y. So the component at node n in the member direction will be called dn, and it will be the summation of these two components. Okay, just a quick one here to make sure you can understand what I am saying. Okay, so if we go to the painting again, so here we have, for example, this is our member, and this is our x coordinates and y coordinates in global. So the red x and y are global coordinates. So what we are doing is we assume that we have a displacement at node n here in x direction global system called dnx. And we know this is called theta x. So if we analyze the force in the member direction, this is the member direction. So this is x dash. Okay. Sorry, guys. Can you see it now? Okay. Thank you. So the variable dotted axis is called x dash, and the perpendicular will be y dash. X dash and y dash are called local coordinates. Okay, so we just need to find a relation between the global and local coordinates. Okay, so if we have a look here, if we have dnx, this is the displacement in global system in x direction. So if you want to get the component, to analyze the component in the member direction. Okay, this component, I will call it dn1. Can you find dn1 for me? dn1 will be dnx cosine theta x. Okay, if we do similar thing but in y direction, in same slide, in same graph. So if I add a displacement here and we call it dny. So if we want to find this the component in member direction, I will give it purple, sorry, the pink color. Okay, we know that this theta is theta y. So how can we find the pink component? The pink component, I will give it simple dn2. So dn2 will be dny cosine theta y. So how much is the resultant of dn2 and dn1? The resultant will be called dn equal to dn1 plus dn2, and it will be dnx cosine theta x plus dny cosine theta y. Okay, so we have dnx cosine and dny cosine. Okay, do you understand from where we get to? So you don't have to derive this yourself, but at least you know where it come from. So we'll return back to the slides. Okay, so in similar manner, if we apply also at node F, so we will have dfx cosine theta x and dfy cosine theta y. And using these two, you can replace cosine theta x with lambda x, cosine theta y with lambda y. Okay, so after replacing the theta, cosine theta x and cosine theta y with lambda x and lambda y, we have dn and df equal to lambda x, lambda y, 0, 0, and 0, 0, lambda x, lambda y times dnx, dny, dfx, dfy. Okay. So how can we get this? This is from the previous equation here. What we have done is just making this in a, instead of algebraic equation formula, we convert it to a matrix formula. Okay. Do you know how to do this? Or do you understand from where it come? Because we have how many parameters we have? We have 4: dnx, dny, dfx, dfy. So what we have done is just make the 4 parameter. The first two are only existing in the first 2 columns, and the second two are only available in the third and fourth column. So it will be written like this: dn df. What is dn and df? Dn and df are the local displacement. Sigma x, sigma y are cosine theta x, cosine theta y. dnx, dny, dfx, dfy are the global displacement at node n and node f. Okay, so this formula is important to us, so please keep it in mind. This is how to convert from global to local coordinates. So if you have the global coordinates, it will be multiplied by t, which is called transformation matrix, equal to the local coordinates. So here, okay, so share the screen again. Okay, so for this one, we have finally dn, df. These are called local displacement, or displacement in local coordinates, will be equal to lambda x, lambda y, 0, 0, 0, 0, lambda x, lambda y times dx, dnx, dny, dfx, dfy. The orientation or the order of this members or these elements are important. As you can see, firstly, this one is the local displacement matrix or vector. This is called transformation matrix, and this is called global displacement vector. As you can see, this one is 2 by 1 vector. This is 2 by 4 times 4 by 1. Because this is the multiplication of matrices, you should have this in mind all the time. What is the common here? These 4 are the common things between these two matrices, and this will be the result. So the result should be 2 by 1 because we have here 2 rows and here 1 column. So the result should be 2 by 1, and which we have now. Okay. For the numbering, this DNF, DN 1, 2. Here, this lambda x, lambda 2, 1, 2, 3, 4. And here, the numbering is 1, 2, 3, 4. So what always will be number 1? X direction for node 1 or DNX. So you cannot change the numbering or the orientation of the unknowns or the displacement. Okay. So this should be in X direction, displacement in X direction, displacement in Y direction. This for node 1. Also, this is X and Y for node 2. So the numbering cannot be changed. Okay. So if we go back to the slides, trying just to make it easier for you. So if we go back to the slide, this is our final equation, D equal to T times D, where T is the transformation matrix to transform the 4 global displacement D into the 2 local displacement D small. Okay, T is referred to as the displacement transformation matrix. So T is called displacement transformation matrix for a truss. And how can we write it down? T is equal to lambda x, lambda y, 0, 0. And the second row is 0, 0, lambda x, lambda y. Okay. Now, after we get the displacement in global and local coordinates, now it is the time for global and local forces. So how can we find the how can we transform the forces from local to global? Again, Q capital is the forces in global system. Q small is the force in local system. So in similar manner, in similar procedure like the displacement, to convert from local to global, we will have same cosine x and cosine y. So if we look at figure A and figure B, for figure A, we have Qnx and the Qny. So Qn is the force in the member direction. Qnx and the Q1 are the component in x and y direction. It is like analysis of forces, algebraic analysis of forces using the angles trigonometry. So if we have Qn, how can we find Qnx and the Qny? Qn cosine theta x. Just make it quickly here. Okay, if we have this member, again, this is, if we have a member, so again, this is our x bar or x dash and y dash local axis. This is x and y global axis. The angle theta x, this angle is theta y. Now, if we have a force in the member direction, this is called, or we give it the symbol Qn. Okay, so Qn is the force in local system. If we have Qn, how can we find Qnx and the Qny? This axis is, if we extend this to axis, so this is theta x and this is theta y. So the force in x direction, this component will be called Qnx, and this is called Qny. Qnx will be Qn cosine theta x. Qny will be Qn cosine theta y. Okay, so x cosine theta x, y cosine theta y. Okay. So these two components are global member forces or global forces, and this two Qn, or this one is local force. Qx, cosine theta x and cosine theta y will be the transformation matrix. Okay, so this is how to convert from local to global forces, similar to the displacement. Okay, so if you have a look here, so equation 6 and 7, similar idea. We get Q, if we have QF, so we can find QFY capital, QFX capital. Okay, so now the force transformation matrix, if we are replacing cosine theta x with lambda x, cosine theta y with lambda y, we will have Qnx, Qny, Qfx, Qfy, lambda x, lambda y, 0, 0, and the other column is 0, 0, lambda x, lambda y times Qn, Qf. What is the comparison, or what is the difference between this equation and this equation? What is the difference between the transformation matrix for displacement and the transformation for forces? Can you tell me? What you can see on the left hand side for this equation, equation number 8. Is it local or global forces? So the difference is, in this equation we have the global forces on the left hand side. So the global forces will be the transformation matrix transpose times the local forces. But in the first equation for displacement, we have the local matrix on the left hand side, the local displacement on the left hand side. So it will be the transformation matrix in its original orientation times the global displacement. So this is the difference. In this equation, equation 4, we have the local matrix on the left side. And in this equation, we have the global matrix on the left side. Okay? Because we are using these equations to transform between both of them. Like if you have the local, you can get the global. If you have the global, you can get the local. Okay? So in this equation, equation 8, we can write it as Q capital, the forces in global, equal to T. It is similar to the transformation matrix of the displacement, but it is transposed. So it is called T transpose times Q, where Q small is the local forces. So T to the power T, or T transpose, transform the two local forces Q small into the four global forces Q capital. This is called force transformation matrix, and it is the transpose of the displacement transformation matrix. Okay, so if we have a look here, Q small, sorry, just a revision of what we have. So we have displacement, which is equation 4. From equation 4, if you go back to the slide, we have dN dF equal to lambda x, lambda y, 0, 0, 0, 0, lambda x, lambda y, times dxf, dx, sorry, dxn, dyn, dxf, dyf. Okay. For forces, we have qnx, qny, qfx, qfy, equal to lambda x, lambda y, 0, 0, 0, 0, lambda x, lambda y times q small n, q small f. Okay, so this is a comparison between transformation of forces and transformation of displacement. So here we have local equal to transformation matrix times global. Here global equal to transformation matrix, but the transpose of it. So transformation matrix transpose times the local. So generally, and this is a general rule, to get local from global, we need to multiply the global times the transpose. Sorry, the transformation matrix. Okay, to convert from global to local, sorry, from local, if we have the local and we need the global, we will multiply by the transpose of transformation matrix. So what you need to keep in mind, you need to keep in mind this matrix. This matrix you should know and you should keep in mind. What is the transformation matrix for a truss? So T for a truss is equal to lambda x, lambda y, 0, 0, 0, 0, lambda x, lambda y. So this equation, this transformation matrix is 4 by 2. 4, sorry. This transformation matrix is 4 by 2. 2 by 4, sorry. 2 rows, 4 columns. So we have 1, 2, 3, 4 columns and 1, 2 rows. Okay. So this is called transformation matrix of a truss. Okay. If we want to get the transpose of this equation, of this matrix, how can we find the transpose of this matrix? Do you know how to get the transpose? This was in the revision of the first lecture. How to get the matrix transpose? Do you know? T transpose of a truss will be 4 by 2. 4 by 2. Because what we are doing to get the transform, we are making the row column and the column row. So if we are getting the transpose, this row will be a column. So it will be lambda x, lambda y, 0, 0. The second row will be the second column will be 0, 0, lambda x, lambda y. So this is how to get the transpose. The row become column and the column become row. Okay. So this is the transpose and this is the transformation matrix itself. Okay. So this is generally what we have done during this part of the session. And hopefully you can understand what is how can we get this, and if you have any question, please let me know. Do you have any question? Do you have any question up to now? No? Do you want to have a rest for 10 minutes? Can you hear me? We will have a rest for 10 minutes up to 12 a.m. in Adelaide time. So 10 minutes and we will be back. We'll be back. Just a quick break and we will be back. Okay? Thank you. So before the break, we reached the force transformation matrix, which is quite similar to the transformation matrix for displacement. So we find that Q capital is a force in global system equal to T transpose times Q small, where Q small is the local forces or the forces in local system. T transpose is the transpose of the displacement transformation matrix, or we can call it as the force transformation matrix. So in brief, remember global stiffness matrix. In this slide, we will know how to determine the stiffness matrix for a member, which related to the member global forces component Q capital to its global displacement D. So this is how to connect between the global forces to the global displacement. So if we substitute from equation 5 into Q equal to Q dash times D, we have Q equal to Q dash times T times D. If we go back to question 5, this is question 5. Question 5 is the connection equation between D and D small and D capital. So D small equal to T times D. So if we go back to our slides here, so we know from last week lecture that Q, the forces equal to the stiffness matrix in local coordinates times the displacement. So Q small will equal to Q dash times T times D. Okay. And if we substitute equation 10 into equation 9, equation 9 is Q capital equal to T transpose time Q. This will give us the result as Q capital equal to T transpose K dash T transpose D capital. This is just to find a relation between Q capital and D capital. So Q capital is the forces in global system, D capital is the displacement in global system, and T transpose is the transformation matrix transpose. K dash is the local stiffness matrix of the member. T is the transformation matrix. Or we can write it in the form Q capital equal to K times D, where K is T transpose times K dash times T. So K is a stiffness matrix in global system. K dash is the local or the stiffness matrix in local system. T transpose is the transformation matrix transpose. T is the transformation matrix as we learned from the previous slide. Okay, to summarize or to convert this to a matrices, we have the matrix K is the member stiffness matrix in global system, and T transpose and K dash. So we have K small will be T transpose lambda x lambda y 0 0. Second column is 0 0 lambda x lambda y. K dash from last week is AE divided by L times 1 negative 1 negative 1 1. T is lambda x lambda y 0 0, and second row is 0 0 lambda x lambda y. Can you do this matrix multiplication? Or you can't? This matrix multiplication need to be done at 2 steps. You have to, if we call this A, B, C, so maybe we do A times C first, and then the product we multiply it by A. So the final result for this matrix is K equal to AE by L times lambda x square, lambda x lambda y, negative lambda x square, negative lambda x lambda y, and so on. Okay, as you can see, the location of each member, first the matrix in global is 4 by 4 because we have 4 elements. for displacement, 2 at each node, and the location of each element symmetric is referenced with each global degrees of freedom. Okay, just to make this a bit clearer to you. So the final from last week, we know that K dash or local stiffness matrix of a truss is equal to AE divided by L times 1, negative 1, negative 1, 1. Okay, so this was the local stiffness matrix for a truss. Today we have K, but the global stiffness matrix of a truss will be equal to AE divided by L. And it will be, instead of 2 by 2, it will be 4 by 4 matrix. What are the 4 elements we have? Lambda x squared, lambda x, lambda y, negative lambda x squared, negative lambda x, negative lambda x, lambda y. Okay, so this is our first row. So this 1, 2, 3, 4, 1, 2, 3, 4. So this 4 by 4 element. Second row is lambda x, lambda y squared, negative lambda x, lambda y, negative lambda y squared, negative lambda x squared, negative lambda x, lambda y, lambda x squared, lambda x, lambda y, negative lambda x, lambda y, negative lambda y squared, lambda x, lambda y, lambda y squared. Where, don't forget that lambda x is cosine theta x, lambda y is cosine theta y. Okay. If we have a look here, this is a symmetric matrix. So if you see this diagonal member, our diagonal chord, so the half on the top is similar to the half on the bottom. So you don't need to know all of them. And there is a relation between, if you look at column 1 and column 3, so column 3 is negative of column 1. So if you know column 1, negative times negative 1 it will give you column 3. Also, column 2 is the negative of column 4. So negative column 2. Okay. So this is how to recognize the matrix. So we have symmetric matrix. This is a symmetric matrix. This is a symmetric matrix. And we have column 3, negative column 1, column 2, negative, sorry, column 4, negative column 2. Okay. And this is based on that we have, if we have a global inclined member with global coordinates. So we have 4 degrees of freedom. If node 1, node 2 says displacement 1, displacement 2, displacement 3, and displacement 4. So 4 by 4 because we have 4 degrees of freedom for a member in global system. And again, this is our global system, X, Y, and this is our local system, X dash and Y dash. Okay. Do you have any question for this one? So this is the final output we need in this lecture, equation 15. Okay, if you look at equation 15, so this is the final output we need. K global equal to AE L times the matrix we have. Okay. Now, for the structure stiffness matrix, once all the member stiffness matrix are formed in global coordinates, we can then assemble them in the proper order so that the structure stiffness matrix K, so K capital is the global stiffness matrix for the whole structure together. So K small is the global stiffness matrix for each member, and the K capital is the global stiffness matrix for the entire truss or the whole truss. This can be done by designing the rows and the column matrix by four codes numbers nx, ny, fx, fy, where n and f are the end and start points. So n is the start point, f is the end point. The structure stiffness matrix will then have an order that will be equal to the highest code number. So if the highest code is 4, so it will be 4 by 4. Okay. If we have like truss of 4 members, so it will be 16 by 16, something like this. So the stiffness matrix of the whole structure will be the highest order of the numbering. Okay. So, and this will represent the total degrees of freedom of the truss. So if we have 8 degrees of freedom, so it will be 8 by 8, 4 degrees of freedom, 4 by 4, and so on. Now we have an example. In this example, we need to determine the structure stiffness matrix for those two member truss shown in figure. Do you want to think in it? Just we need to find the global stiffness matrix for the truss. We'll give you 5 minutes to think about it.
自己动手就知道哪个地方你知道是吧？每次一挑一目了然，一写一篇毛病。